Yeah, we will start in a few minutes. Um, I am still expecting a few people to join, so I'll give it another 3-4 minutes. Get to work. Get to work. Okay, ladies and gentlemen, it's 2:15, and we're going to start. Welcome. This is a course, workshop on the implications of encryption in public policies. What I will do is this coming hour or two is try to stay at a relatively high level, but still give you a little bit of a broad perspective of what encryption is, why it is used, how it works, but not in the mathematical details, why the mathematics are actually important, and so on and so forth, and give you a little bit of an insight all the way at the end of what we call encryption debate. What are the things that are actually being debated? I have an agenda for today. Oh, this is going to be confusing. Yeah, so I'm going to talk a little bit about the Internet Society. We've been together in this room for quite some time, but I have a little movie to show about what we do as Internet Society. Then I'm going to provide you a little bit of context. What is the context in which encryption is used? Talk a little bit about what encryption is, how it works, when and why we use encryption, a little bit of myth busting, so to speak, common things that we hear, and we talk about encryption and public policies, the pieces that I just referred to. There might be some repetition here, back and forth. If I realize that, then I might skip a couple of slides. This is the first time we give this workshop in this form. So it's always a little bit of exploration of how to present the material. I love this to be interactive. If you have questions, please ask, no matter how trivial or how technical they are. If you are confused, don't hesitate to ask. We are among friends. Well, maybe we should stop the recording for a moment when you ask a question and it's really dumb, but it's really ask questions. We should learn from each other, and questions are part of that. So the Internet Society, if all is well, this is a movie. Oh no, it's not. No, well then you don't get to see the movie. Internet Society is our mission, I talked about this morning, is to provide a secure, trustworthy, and open internet for everyone. And when I talk about the internet, I'm really talking a little bit more about the infrastructure, the networks of networks that provides connectivity globally. And all the technologies that enable people to talk to each other or services to communicate. And that's encryption is one of those infrastructural components that make part of that. We are an organization with 104,000 members, going 105. We have 87 organizational members. Those are companies, they pay us money. The individual members, by the way, do not pay us money. We have 126 chapters and special interest groups, among which a very active chapter here in Lebanon, and some members of the chapter are among us today. For full transparency, we are not paid only by these corporate entities. We are also paid through the selling of domain names. .org, the top-level domain .org, is operated by the Public Interest Registry, which is a subsidiary of the Internet Society. And that allows us, that is the Internet Society, like I'm an employee of, and the Internet Foundation, which is a grant-making affiliate, so to speak, sister, to do our good work. So that's for full transparency. You always know, follow the money, and that's where it comes from. So we are an independent voice. I always say we get our money independently. That makes us an independent voice. Even though we have members, we can afford to lose them. So focusing on encryption. Oh, by the way, we don't want to lose members. We want to get more members. So if you're interested. Yeah, there's a question in the back.
May I add one? My name is Jack Bakayev, and I'm from Internet Society Lebanon chapter. So I would just add one idea about what Olaf said. So either join the chapter in your country. If you don't have a chapter in country, you're welcome to join any chapter in a neighboring country. And in Lebanon, I think you're all welcome to join the Lebanon chapter if you wanna be involved in Internet Society activities. Thank you.
Yeah. The chapters are independent entities that basically commit to trustworthy, secure, and open internet for everyone. Good. The big why. Why are we talking about encryption in the first time? Well, here's a little bit of an example. I'm pretending to be an executive of a large financial firm. And these are some of the transactions I have during a day. I pretend I'm an executive. That's always nice to pretend. I received a message from my CFO. I've been working on this merger, and we received a message that the workings has been complete, and we are about to announce that merger. We're about to sign the paperwork and get going. You understand that this type of information is highly confidential. A merger is something that you can use for buying stock and shaping the market. This type of information is highly confidential. How do we communicate that? Well, usually through applications like WhatsApp or Signal or Messenger or what have you. You know, one of the plethora of messaging apps. A little later, press release goes out. So, okay, we've got that covered. It's now in the public. And this has been picked up by major financial outlets, and the stock markets are roaring. That news. What if somebody was able to change that news? Also to their financial benefit. What if somebody could hack a website of a major newspaper or intercept the traffic and change it? What happens then? Well, again, here, security methodologies like encryption can protect you against that. So I go into the building. And if I go to my office, I check in. And there might be a cloud service involved in me checking in. I check into the system authenticates to a cloud service somewhere on the cloud to check my credentials, see if I'm still an employee, those type of things, and then enter the door, open the door. What if that traffic could be intercepted and changed? Another part where in a normal business world you could have where if the transaction is intercepted, modified, or read, lots of things can be learned about the company, or even attacks can be placed, like a physical one. Video call, calling with your colleagues. What if somebody can listen in about your strategy? Or, you know, if you talk to your minister, what happens if somebody can listen in? Okay, confirm the deal, the closure of the deal can make the company $2.5 million in this case. How does that work? You know, the confirmation of a deal is that the digital signature that is placed somewhere. And we talked about digital signatures this morning. This is the type of infrastructure that you want to have secured. And finally, intensive day, your smartwatch reports that you are stressed. Is that information that you want to have everybody know that you are stressed? And again, this is information that traverses the internet. And in all these cases, you want this information hidden from other actors, from third parties. This is information that's between you and the counterpart that you are talking to. People say, you have nothing to hide. Well, there's a bunch of things you want to hide in these transactions. And that is where encryption comes in. Oh, I forgot the personal assistant reporting stuff, but let's not go there. If you look at security in the general sense, then security is a bunch of things. There's security in the digital domain, and there's all kinds of things that contribute to it. Confidentiality, authentication, access and authorization, integrity, and availability are those keywords that come in when you talk about security. Now, strong cryptography, so the math of scrambling things and making them secret, and also the math to create digital signatures, that strong cryptography feeds into all of these points. And of course, you have physical security, detection, quality assurance, vulnerability management, best practices also contribute to security, but perhaps not that much with the aid of strong cryptography. So when I talk about encryption, I talk about strong cryptography, which is one bag of tools that we use across many types of security mechanisms. And when we talk about encryption, really, it's mostly confidentiality, integrity, and perhaps a little bit of authentication, which is part of what we talk about when we do normal encryption. Okay, this is perhaps one of the deepest technical slides, or at least I think it is. So, just another example. Every company today will use data center of some sort, either self-hosted, either hosted by one of the big cloud companies, or what have you. The feature of a data center is that they run with so-called virtual machines. So when you log into a data center on a machine that you own in a data center, you're not logging into a machine you own yourself, like a piece of iron with a disk and a CPU and all the stuff. No, you're logging into a virtual machine that runs on the same piece of iron with a bunch of other virtual machines. And what happens on your virtual machine, you of course want to, keep away from the other virtual machines. And it is the fact that that when things are in a data center, they are in shared infrastructure. So when you deploy databases, when you deploy and store data of your citizens in data centers, you want to make sure that that data, when it's stolen in some way, it's not readable. Encryption saves you from data being readable. And here is a statement from an ENISA report. In virtualized environments, you really need that security because of the sharing of infrastructure. Man-in-the-middle attacks become highly critical in virtual environments. What is a man-in-the-middle attack? Does everybody know what a man-in-the-middle attack is? Haitham, you can. I'm not putting on you on the spot for this. I know that. You can explain what a minute, just to keep it a little bit light.
Sure. Man-in-the-middle attack is a man sitting between two speakers, or let's say two clients, and he's listening to one, taking that message and convert it according to his needs, and then send it to the other guy, which it is the receiver. So he's communicating between the sender and the receiver, and not only intercepting, but he's changing the content to his benefit. So maybe he's trying to fall out between the two, or maybe he's just listening, passive or active, whatever he chooses, but he's right in the middle between two kind of speakers, sender and a receiver.
So a man-in-the-middle attack doesn't only listen to the traffic, it also modifies the traffic. Yeah. And one of the things that protects against man-in-the-middle attacks, modifying things, is what we call integrity protection. Integrity means that the content of a piece of data, you can validate that that has not been changed. Yeah? So integrity protection helps you there. And I'm trying to do the next slide, but the thing doesn't respond. Oh yeah. So this is sort of an idea of a data center network where you have a piece of iron. This is really a computer, like you would have a laptop, so to speak, but then on industrial scale. There is hardware, there is software, and there is virtual machines. And it might be that you rent this machine, this machine, this machine, all the brownish ones, and your competitor or somebody else rents these machines. Now, what you don't want to do is have data leakage between the two, but sometimes there are bugs in the implementations of these things. The term hypervisor comes to mind when you talk about the implementation. And if there are bugs, data can leak. And of course, there is a network connecting all these machines. And if things go over that network, maybe they can listen into. And so these are places where encryption becomes valuable as a means of protecting your average data, day-to-day kind of stuff. Note that I'm talking about things that are relevant in your production as a government. This is where your tax authorities run their software. This is where, well, we talked about various things this morning, driver licenses. In modern days, that is where your services run. And so, thinking about what do I protect, how do I put protections in place, encryption is always part of that equation. Protecting the data at rest and protecting the data in motion. And I'm going to talk about both concepts. So yeah, encrypted content and virtual private networks is what you need. And the key word with this word fell before, zero trust security design. This is the real keyword if you talk about anything, any design that involves networks. Any design that involves networks, and in particular the internet, you take a zero trust design. And that means you don't trust anybody. You only trust yourself. And you might trust the person you are doing business with, but everything else in the environment is hostile. That pink virtual machine, that was on the same machine as my virtual machine, that's a hostile machine. And you have to think about how could that machine attack my machine? And of course, the designers of these virtual machines and the designers of the infrastructure that makes that happen do that for you. But even then, maybe there are additional measures you can take to protect your data. Zero trust security design is about making sure that you understand your whole environment and treat it as potentially hostile. Other actors in the system are not trustworthy from a technical standpoint. Of course, in security, you always try to protect yourself also using legal means and contracts and processes and procedures. But technical design is best when you say, I don't rely on these things. I don't rely on specific policies being in place. This was a point that Robin made this morning when he talked about trust. And if I say, how about the web? Well, the web is that hostile place. The web is that place where if you type, if you read, if you speak, potentially everybody can read and see what you do. That's where encryption comes in. There's a whole lot of information on this slide. But encryption is not something new. People have always tried to hide information from others. In military conflicts and in state secrets, always been the case that secret messages were used, either by hiding things in a container or using a cipher. A cipher is a way to transpose a script into something that is unreadable. And the cipher is then also very, very secret, so that the receiver doesn't understand what they get. I'll have an example later. There's, all kinds of things that have been developed, but in the modern era, you could say that sort of the first thinking about digital information and how to transcode readable data into some other format came with the Morse code. Then we had letters, we used to write them on a page. the Morse code transformed that into beeps and longer beeps, points and dashes. Beep, 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 beep. Save our souls. Everybody knows this. And what really happened is that the encryption grew and grew and grew with the onset. So we had the Enigma machine, the famous Enigma machine, which was a electronic mechanic device which would actually transpose tight-in letters in a very ingenious way, which was very difficult to rely on. Doing cryptography, because this is the art of cryptography, having what we call a plain text, something that everybody can read, presuming that you know the language and so on and so forth, to something that nobody can read, that's an art form. And what happened in these times was that the attacks on ciphers, so the way to do this transposition from readable text to this cipher text, was always subject to trial and error, just trying different letter combinations and see if you could get to the original, or doing statistical analysis. If you have a very plain translation from one language to another, then it's very easy to a ciphertext. Then it's very easy to just count the amount of occurrences of letters and know this is an A, this is an E. You know, just use statistical tables.
Yeah, I was saying that the Arab had a cipher as well in the past using poetry. So they would send military commands or instruction in form of poets. And that's their way of doing, let's say not steganography or cipher, but only a few who will understand the real meaning behind that poet, like
Yep.
an instruction. So that's just an informal.
And so there's a very important distinction here. A cipher is a way to transpose one text into unreadable text. That's a cipher. What you are talking about is what we call code words. Like the baker delivered 20 pounds of flour at the grocery store. That might mean a ship of coke worth 20 billion has arrived in the Rotterdam harbor. That's code, but encryption is really the transformation. And so until the digital era, attacks on cryptography were usually trial and error. So trying to see, trying to understand based on statistics and so on and so forth, what was written, and that became computationally intensive. You had to have some prior knowledge, and the best known story of this is a highly complex machine with rotors that rotate with every key press and then produce a different output based on an input key. There's a beautiful book by Singh, The History of Cryptography, which I can recommend to everybody, which describes all this. This could only be broken by computers. And only in the mid-80s, I believe, mid-70s or mid-80s, it was that high-grade cryptography became available through the use of computers for the masses. Only then, people understood that some mathematical formulas could be used to create encryption. So that's only from the mid-80s that encryption, powerful encryption, became available to the masses. And that changed a lot. Let's not be dubious about that. It changed a lot. Until here, encryption was basically either very playful or powerful and in the hands of states. In the modern era, it has been highly democratized. The use of encryption has been highly democratized. And now we're in another time and era where there is talk about quantum cryptography, the use of quantum computers to crack software, but I won't go into that now. I can talk about it a little bit later. Questions so far?
How many messages of the Enigma they actually broke so far?
I have no idea.
I think they still have number of them. They are not broken yet.
Could be. I don't know. No, I don't know. Wikipedia is your friend for this. I'm looking at the translators whether they. No, it's all good. Good, fine. You know, I'm using all these technical terms, and that might be tricky at times. So what is encryption? Well, encryption, I already told you, but it's the process of encoding or encrypting. That's the same, those are synonyms. Encoding or encrypting data so that it can only be read by somebody who has the means to return it to the original state. Encryption, decryption. Those are the two terms that come with it. It is a crucial feature of a secure, reliable internet and helps us ensure the safety of sensitive data. When the digital era started, our volume of information that we pumped around increased significantly, and therefore also the need to secure that data. It was easier to get by. It used to be the case that, you know, things on paper, you have to physically get to a piece of paper. But when it's shipped around the internet, you can hack somebody's computer, you can get into a system, you can snoop on the internet and just get that information. So the digital era has changed that need for information. You encrypt the data with what we call an encryption key. And if you have the correct key, you can also convert the encrypted data back to the origin. So just a side note. The math that is used for encryption, no, the math that is used for this type of encryption was already used, say, in previous times. The best way of encrypting a message, if you want to send a message to Hytham, the best way is if you have a book with random numbers, completely random numbers. And what you do is you basically take a letter, you turn that into a numerical value in some way, and then you combine that with the first random number in the book, and out comes another random number. And if you take the first random number out of the book and combine it with this encrypted ciphertext, then you get the original again. So if you have a book with random numbers and you have exactly the same book with random numbers, then you can encrypt and decrypt. And it used to be the case that military intelligence staff was present to generate these random numbers. Those would be usually ladies that have one of these bingo machines, and they would turn the crank and get a ball and write down the number, put the number back, and there was a procedure. You have to turn 2 times that way, 2 times that way, in order to get complete randomness. But that is the safest way to encrypt messages. It means that you need to have a key that is as long as the text that you want to produce. And it's very cumbersome to spread that key around. And we're going to look at that later. That's the best way. That's still the ultimate way to encrypt messages. And underlying the math is that's still the way that people do it. Conceptually. Anyway. We have data at rest encryption. I already talked about that. And it's about data that is stored somewhere. So this computer, this Apple computer, has file vault. File vault is a mechanism to encrypt the data on the disk so that if I lose my computer and somebody else opens it, it's only scrambled data. It looks completely random. So if you have a computer, make sure that you have disk encryption on so that's protected against theft. Somebody steals your laptop, you don't have to be worried. Yeah? So data at rest encryption, databases, file systems, disks, and digital objects, that's where you apply that. Think of your backups. You want to encrypt your backups so that if they're stolen, nobody can read them. But you also want to keep the encryption key to yourself so that you can decrypt the data when the backup is needed. And of course, we talked about ransomware. That's also data at rest encryption used by the bad guys. They do the backup for you, so to speak, or the encryption for you. And of course, the best way to protect against ransomware is to have good backups. That's still, if you have good backups, you can always restore your company. If you've tested that and you're confident about your backups, you don't have to pay your ransomware. But who is? I don't know. I just described this full disk encryption. I don't have to read this, but if people use Apple computers, they know about this, and also Windows computers have these properties. Is everybody still with me? Are there questions so far? Am I going too slow? Am I going too fast? Could I speed up?
So far, so good.
So far, so good. You're the clients. If I need to speed up, I can do so. Encryption of data in transit. Data in transit is information that is moving through the internet. It can move from here, from my computer, to the local hotspot, which I think is over there. It can then move through the building, through all kinds of cables which can potentially be tapped. It then goes to the internet, goes to the data center. I already talked about data centers that can be hacked. The way that you protect against this is by encryption again. In fact, the connection between my laptop and this device that is on the ceiling here is encrypted on a low layer, on a layer. Okay. Internet technology is always layered. So things build on top of each other. The internet itself is built on top of this Wi-Fi connection. So the Wi-Fi connection is a layer that has encryption. The internet protocol itself, unfortunately, doesn't have protection. You have to add that on top in the application layers, as we say so. And here are some names of these application layers. You can encrypt your IP traffic by deploying IPsec or deploying a VPN. But there are different, protocols that we use in the internet to encrypt. HTTPS is secure web traffic. SSL TLS transport layer security is a very generic protocol. It's actually one of the protocols that is used to secure HTTP, but it's also applied in other protocols on the internet. It's one of the building blocks, the encryption building blocks that is used for many types of interactions on the internet. And that's an important point, by the way. Once you break this building block to compromise HTTP, you break the building blocks for lots of other applications. Anyway, this is the protocol soup that you might encounter when you talk to people about security. So I'm not asking you to remember all these things. I'm sort of pointing you out a couple of acronyms that you might run into when you see this. An important term here is, that's very, very nice of you. An important term here is end-to-end encryption. So, as I said already, traffic goes in many hops. And sometimes only one hop is encrypted. Like the connection between my computer and this white thing on the ceiling might be encrypted. But then the rest of the path might not. And if you send an email, it might be that my email is protected from going from me to the sending email server, from the sending email server to the receiving email server, and from that server to the recipient. But then it's unencrypted on those two stations that it hit on its path. Those can still see the message. That's not end-to-end encryption in terms of the system of sending email. So it's very important, if you talk about end-to-end encryption in the context of messaging systems, end-to-end encryption means that when I send something from my phone, and here we talk about trust and trustworthiness, I can trust that only the intended recipient can read it. And there is protocols and math in place to give me the trustworthiness of the system. This was the difference I talked about this morning. That system is actually, there is mathematical proof, so to speak, that warrants you that system to be trustworthy. Now, you might still not trust it, but it's actually trustworthy. So this is the example of end-to-end encryption. It might be that you use Gmail to send mails, and indeed the communication between you and Gmail is secure. You can see that when you have a little padlock here, which is not on the screenshot. But it might still be that Google is scanning the message to train their AI. I don't know, I haven't read terms of service if that is really the case, but that could be. And of course, this goes to a recipient mail server, and that could be read there as well. In a different jurisdiction, law enforcement might actually pull that data off. So what you actually want to do is secure that that mail by signing it and encrypting it locally and then sending it. So how does encryption work? Well, I already said that a little bit. You start with clear text, then you have an encryption mechanism, then you have a ciphertext, then you have a decryption mechanism, and then you have clear text. And at the moment you're here, nobody can read your message. So in a safe system, this is the boundary of what is under user control, and this is the boundary of what is under the other user control, and this ciphertext is only visible on the networks, on the internet, for instance. And again, I have some examples here. Yeah? A critical feature, air traffic control, where encryption is important. Video calls, air traffic control, e-voting, all those type of things where confidentiality is important, you use encryption.
Olaf, we have a question.
Yeah.
How does it happen when they say that don't believe that WhatsApp or Facebook have your messages encrypted and they have access to your data? So what is it that is going on in this situation?
I shall be honest, I don't know what the current status of WhatsApp is.
Previously, when they used to say
Yeah.
it's don't believe that it is end-to-end.
Yeah, what happened was what I was talking about just a minute ago was you had hop-to-hop security. So I take my phone, I send a WhatsApp message, and what happens is that WhatsApp message is then delivered to the server, to a server owned by Meta. And there, because there is encryption on the link between Meta and myself, that part is encrypted for anybody else, but then Meta gets the message and forwards it to somebody else. And then that part between the somebody else, your friend, and Meta is not encrypted. But Meta, as the man in the middle, so to speak, as the service provider, has access to your information. So you have to trust the policies and procedures and the accountability of Meta, Facebook, in order to have assurance about the confidentiality of your network. That's not a zero trust model. You have to trust something to happen. And in an end-to-end system, and I believe WhatsApp is there, and I'm pretty sure that Signal, for instance, has this, or no, I'm sure that Signal has this. Signal does some work on the background, but you are the only one that gets to see your message, and your friend is the only one that gets to see the message. So even though everything passes through Signal's infrastructure, or at least is negotiated through Signal's infrastructure, it's only ciphertext, and they don't get to see it. And that's the power of end-to-end encryption. When we talk about end-to-end encryption, that's the certainty that we have. I'm looking at the clock. We've been okay. Now I'm going to do a couple of slides and then
May I?
yeah.
Okay. So when you have this end-to-end encryption and you have a key, and this is we think that we guarantee confidentiality between the sender and the receiver, and in some countries, in some regulations, you have to deposit the key at some place, so they can go back to decipher and decrypt for judicial or whatever reason. Okay, so where's the guarantee here in keeping the?
There's not. Well, there's not in the sense of that you only have procedural and legal guarantees. You have to believe the trustworthy. You rely on the trustworthiness of the government where you deposit your key. So this is not a zero trust model, and zero trust models are usually the better idea on the internet. Huh?
So we could go back to trust in governmental services.
There is a party where you have to trust the third party, and in this case, it's a government. Yeah, that's the case. And unfortunately, we have seen that even the most advanced administrations that make security their core business have seen data leaks. I'm talking about Snowden. NSA is the most advanced security agency in the world, if I may, or let's tone it down a little bit. One of the most advanced. And they managed to lose their secrets. That doesn't instill trust on that institution, so to speak. And the fact is that every time that you trust, that trust is not usually, but is often violated in some way. And specifically when you have something as valuable as a key to the communication kingdom, you are an incredible target for hackers. So that's another aspect of this person-to-person communication. These keys, you know, shouldn't be the kingdom. They're used once and then thrown away. That's the idea. So I was talking about symmetric encryption. That's the expensive proposition where you have to get the code book, yeah, the books with the random code to somebody else. And that's an expensive thing to do. By this, in communication terms, it's also something where which is computationally intensive. So computers that have to do symmetric encryption. Sorry, no, I'm saying this wrong. This is actually computational very cheap. So this is the way that computers would like to do it. But then the problem is that you have to get that key, which you use to both endpoints. And after the break, we're going to do a game and see if we can sort of simulate that. Now, this invention, the invention of asymmetric encryption, has changed the world. Asymmetric encryption relies on math. And I'm going to do an exercise. Is everybody sharp? Because I'm going to give you a multiplication. I want to have the answer. The first who is answering will get eternal fame and glory. 11 times 15, people. 11 times 15. 165. We have a winner. Okay. I think that took us about 5 seconds and 5 seconds to overcome shyness. Yeah? 5 seconds. Human calculation. Okay. Now we're going to do the same. I'm going to give a number, and you are going to make up what the multiplication is that makes up the number. So you're going to do a division. You're going to factor these two. So 221. 221 is the number. What makes up the two numbers that you use for multiplication there? I can give you a hint. 2 plus 2, come again? No. 2 plus 1 is not divisible by 3, so you can throw away 3. The last number is not 5, so you can throw away 5. The last number is not 2, so you can throw away 2. You know, you go through your prime numbers. I notice that this is already taking more than a minute. This is called factoring, and this is actually, factoring is a difficult problem, also for computers, because what you're now doing, if you're trying to solve this riddle, is you're going through all kinds of numbers and dividing 221 by those numbers and see if it works out. Doesn't matter what the answer is. It's the process that matters. So you're going over this, and this is incredibly difficult. And so the math underneath this turns also to be incredibly hard. Factoring is an incredibly hard problem for computers as well. So if you have two very big prime numbers and you multiply them, that's easy for computers to do, just like it is for humans. But trying to figure out which prime numbers those were is incredibly hard. And the longer the prime numbers, the more difficult it is. That's your key length, by the way. So what people do this is not the correct mathematical description, but say you have two prime numbers, 5 and 3, which together make up 15, then you give one of the prime numbers to the other one, and you encrypt your data with, no, you give the combination of the two numbers to the other one, you encrypt your data with your private key, then you send the message over, and the other key can be used to decrypt it. But also the other way around, if you have a private key, a public key there, a private key here, you can encrypt and send it to the other party. So one key, you have two keys. If you encrypt with one, you can decrypt with the other. And similarly, if you encrypt with this one, you can decrypt with this one. And that enables all kinds of things like negotiating a key between each other. So you don't have to run around with a code book. You can just, set up a communication channel, send each other the code book, and done you are. And the problem with public key cryptography, as this is called, asymmetric encryption, is that you really have to keep your private key private and make sure that whoever has your public key knows exactly who you are. So if I hand my public key to James here, then James validates that it's indeed me that is handing that public key, puts a post-it on the key, stores it securely, and waits for me to return with a message, and then he knows, oh, this is Olaf, so I can use this key. And so you use this. The public key is one that has authentication problems tied to it, and the private key you have to keep private. So when you hear about certification for signing things, you use the same type of encryption. We talked a lot about signing documents this morning. And signing documents is done with this private key and then validated with this public key. And for that, you need to make sure that the public key is owned by the government or by somebody who is approved by the government. I think this is the most important slide of the whole thing from a technical perspective, but this is the underlying stuff. And the math that is going on here is pure magic and extremely hard. And the math that is going on here, there are various types of math by which you can play this trick. This is what we call the RSA type of encryption, the way that I described it. But there's also elliptic curve. Again, I'm posting this because you might hear this at some point. And one of the things that is important once we go forward with encryption is that some of these algorithms, some of the ways the math is working, is vulnerable to the way that quantum computers can crack it. So as I said, the dividing of those two numbers, the factoring of those two numbers is an incredibly hard problem, except for quantum computers. They can easily do this. Or not easily, you need a big quantum computer in 10 years out, what have you. But if you want to keep the secrets, you already have to think about the underlying math. I am going to go into a break because I think we hit a sweet spot. Yeah, I am going to go into a break and then we'll continue after the break. Shall we say 3:30? Yeah? I'll take the time. If I may have a coffee, then that's okay.